Hello together all. My topic today is how to build a race engine. I want to give you, everybody can hear me or see, everything's fine, okay? Yeah. Then the table of content is at first a little bit about the race engine concept, just some words how a race engine could be designed. Then a closer look on engine mechanics. There are only a few examples because of the time. Crank train, then dry sump coatings, then then something about the engine subsystems, especially the intake system and the fuel system as an example. Then I tell you something about different test bench types, how you can handle this the engine on a dyno. Then a short overview about measurement technology. I say normal one, you see later, it's the slow one, and the fast one is the indication. Then, quite important, simulation validation. And at the end, the calibration, the general procedure, a little bit static one and a transient one. Only a few words to my background. I spent some years as a car mechanic. At the moment, 6 years engineering design judging, 9 years in different industry projects. I built 11 years Formula student race cars and some experience in events in the dyno. Therefore, maybe I have the input of the different FS special topics. Okay, here at the beginning, the race engine. It's just an overview to get some ideas. I have there the three main pillars: reliability, drivability, and efficiency, which should mean reliable. You need a reliable concept, a reliable engine. Otherwise, you cannot test it, you cannot use it. I say complexity and lightweight engineering as much as necessary. You want to do a good job, but maybe not too much complexity, not too much lightweight, because everything should work. And a very important point is testing, and testing, which should mean that you need your timelines and you know what you want to do, what you want to realize, but do this really in time. Because, for example, if you have a quite outstanding component, but you cannot test it, maybe definitely it will fail because you need some experience and some optimization. Drivability means, for example, a flat torque curve. That's good for the handling, for the driver, and for the different tracks and different setups. For example, for the powertrain or drivetrain, you can use different setups in the calibration, in a drivetrain with a differential and so on. That you're well prepared. Just an example. If you go, for example, to FSG, maybe some of you know the track, and there is something sometimes hard cornering, then some faster stints. You need a setup, and it's quite bumpy, for example. And if you go to Michigan, maybe it's not so bumpy, and it's more high speed, and therefore you need different setups and different calibrations. Efficiency, overall, just for example, less cylinders. If you optimize your tribology, you can go, we see later something, can go to a lean calibration. This is always efficiency, which means to save fuel, to be efficient. But efficiency can also be reuse of old components. For example, if you build up a race engine or your overall race car and you have really fine working components, you can use them, you can save money and save time. Possible modifications. You can change, for example, you see there the picture of the crank train. You can, for example, change the crank train, which means new pistons for a higher compression ratio. You can make the conrod, for example, longer to reduce your normal forces. You can put in a new crankshaft because of other displacement. Then you see the picture right there. It's an oil pan. You can use a dry sump system for different advantages. For example, to put in the engine lower in the car. And you need trigger wheels to adapt the ECU, calibration, and special things with like an intake or exhaust system because of the package and the restrictions and so on. Okay, now we go on to the chapter engine mechanics. This is just a picture we can see. Some years ago I built up a 4-cylinder. You see there, yeah, with customized pistons. But it just should be an overview that, yeah, you have to do a lot of changes, and you build up your engine at your own. Because if you do it at your own, you have problems, and with problems you can learn a lot. Here, some examples for the crank train. This is maybe the start. At the start you have a stock crankshaft from the manufacturer, and you want to understand it, and you want to make it better or to optimize it for your use. Therefore, you see there, it's a 3D scan. You scan the shaft, the balancing shaft, and for example the conrod and the piston. And then in the next step, you can reconstruct it, because you have the scan, and then you can maybe the balancing shaft like nearly the same. It's just for the CAD optimization, and then you can rebuild it and can optimize to your own shaft or your own pistons. Yeah, if you have it in CAD, then maybe the next step is to analyze it, because you know your forces, you know your refs and all this stuff. You want to change maybe the raw material. Then you do an FEM analyze, and you see where is the hotspot, or is everything is working. Because manufacturing machining is quite expensive, and therefore it's very important to understand the parts. It's just an example, the crankshaft, to understand every part, to analyze it, to do some simulation, and then manufacture it, because manufacture is a lot of resources. Then yeah, you see there, for example, it's now machined. After it's machined, yeah, you have to harden it and to grind it, and then some special things. For example, you put in some wolfram inserts with a high density, high density for balancing and to save weight overall. You see there is also some machining in house, and then here it's balanced on a balancing machine. Some special to the balancing. You see there, these are adjustable master weights, because it means this example is no 6 or 4-cylinder crankshaft. It's a asynchron 2-cylinder, and therefore you need the master weights. Simulate the oscillating and rotating mass of the piston and conrod to balance it in a right way. Yeah, and you see there it's adjustable. That you can adjust the weight of the piston, of the conrod. For example, if you change the piston is, I don't know, 5 grams lighter or heavier, then you can adjust this here. On the right side, you see the crankshaft after the first time on dyno. We want to do some non-destructive testing, because if everything is fine, we want to use it after the tests. And just if there are some gaps, if there is some damage, if there is some vibration damage, just for control and for understand. Then the next, the TriSum system. You see there it's a picture from the overall system with the oil pan. Then there is a pressure pump and a suction pump, something with cooling, and this is maybe the new oil pan. Maybe it's the oil tank. And overall, I just want to tell you about the TriSum. I think we can have, if there are some questions at the end. You can put in your engine lower in the car, because your oil reservoir is not under the engine. Your oil reservoir is beside the engine. Therefore, lower COG. And with the suction pumps, you suck out the oil from the engine. You have a really, really reliable and safe oil pressure under maximum lateral and longitudinal acceleration. It's quite important for a race car, because a race car maybe has high G forces, and you want oil pressure, because without oil pressure you kill your race engine. And only some years, some heights, you can build up the oil pan out of magnesium, for example. It's just for lightweight. Then my whole team use a 2-stage scavenging pump. You also can use 1 or 4-stage. Maybe it's important where you want to suck the oil, and you say it's 1, 2 or 4 necessary. Then in the oil tank, it's just the package work, for example, was integrated the catch tank. And at the end of the day, you don't have to, but maybe for control, for understanding, you can do, for example, some CFD simulation, that you understand if the defoaming, for example, of your tank is working, because you want to separate the air from the oil, because you suck out air and oil, and you want to bring back oil to the engine, not air. Okay, here's a maybe interesting picture, because yeah, I also not understand every system at the beginning, because I also just an engineer and a student, and therefore we put on a, yeah, maybe a visible for visibility, that you can see where the oil is sucked and everything is working. I have, if it works, I hope so, maybe some impressions. Yeah, you see there now the engine is starting, and the suction pump sucks out the oil of the engine, and there is now an engine fired. It's a start from 0 to 4000 RPM. Yeah, I think it's a nice possibility for understanding that you see if is your system working in this way you like it or you designed it. Okay, then so far to the dry sump system. Now a short idea or a short input from different coatings. You can use different coatings in your engine. Maybe some you need, some is nice to have. An example, for example, there you see if you have a damaged bore size cylinder bore and you want to repair it, you cannot hone it and put in the aluminum piston in an aluminum crankcase, because it will not work. Therefore, it's just one possibility. You can use a nickel dispersion coating. You see there, it's on the bore. And then you hone it, then it's coated, and you can put in the piston. This is necessary, for example, if you have to repair your damaged crankcase. Then maybe nice to have, you don't need it. You can put in a DLC coating, for example, on your piston pin. Yeah, it's good for tribology and maybe for reliability. And on the piston skirt, for example, you can put on a graphite coating. You don't need it, but it's good for the in-run, and maybe you can balance your clearance in a right way. But there are a lot of possibilities to use coating. But important is, if you use a coating, use the right coating at the right part. Then intake system. I want to give you a short overview about the intake system, because the intake system is quite complex. At the beginning is, you see there different parts of the intake system, and we use this for understanding and a little bit for validation, because it's hard to do. You do a simulation, then you know, okay, this is the right diameter, this is the right volume, but is it really the right diameter? Is it really the best performance? And therefore you see there different blendums you can put in, make it bigger or smaller, and different runners. At the end of the day, you can change, or you can variable your volume of the airbox, and you can change the length and the diameter of the intake runners from the manifold. And then you can put it on a dyno. See there is the airbox and the dyno. Then you can make different testings with different parameters, and maybe then we change, for example, the material from rapid prototyped to CFRP, and you see there, for example, there are really long straight runners, because then we can shorten or make them longer. And the last step is a full variable intake runner system. To understand maybe the runners a little bit more, you can use a flow bench. You see there is a cylinder head, then there is the way where you suck in or you put it out the air, and it's just for analyze, for example, for intake system ports, or you can analyze different materials of runners and so on. Your measurement data you get is maybe your flow coefficient. It's called alpha K, and you do it for inlet and outlet port. And quite interesting, because you have their waves in the intake system. The air goes not from the left to the right, and then everything is fine. You have there some backward movement. Because of this, you check the inlet and the outlet port, and you check it forward and rightward, because sometimes the air can go back with the resonance waves and so on. You have a look on both ways, on both directions. And then at the end of the day, you see there, the blue one is an optimized intake runner with a new surface and with some polishing and grinding. And the red one is the stock one. And the green is the benefit of your flow coefficient. And this benefit or this values at the end or as a next step you can put in a simulation, and then you have the overall influence. Here is a possibility shown which you can analyze and rebuild to put it in a COD. You can read it there, and I show you the pictures. You have a cylinder head, you have the inlet ports, you put there some like silicon mold, you put it in a cylinder head, and then you can rebuild it and you can put it out because it's quite flexible. You can bend it and then you can get off the cylinder head. Then with some different measurement technique tools, with for example this Faro arm, then you can scan it and rebuild it in COD. And you see there the valves and the surface of the cylinder head. And then you can put this in your COD model, and you have a quite interesting thing, because it's hard to measure it in a cylinder head. Therefore you have to rebuild it, pull it out of the cylinder head, and then you can measure it in an easier way. Yeah, and some values at the end, you see there, the blue one is some static runners, and like mentioned, the orange one is some full variable runners. There you can change just the length, not the volume and the diameter, just the length. But you see there, for example, if a lower RPM, I think you make just the runner a little bit longer, and then you can have a optimization of the torque. For example, I just put out a torque because there are some confidential measurements, but just for your estimation, this is an amount of nearly 8 Newton meters. Therefore, it's quite good benefit at hard cornering at a bus stop or what else, and it's just for improvement of the runners. Then maybe the small, I call it the small subsystems, are also quite important, because your system is only working if everything is working. And therefore a short look in the fuel system. You see on the left side maybe the simple solution. It works, everything is fine, but maybe you want to, as an engineer, you want always to push to the maybe best, or maybe to the solution which you can handle and you can build up. And therefore, for example, the fuel system, we don't talk about money or measurement technique or all this crazy stuff. We just talk about some ideas, and then you can do it in the best way like you want. On the left side you see it's a catch tank, it's outside. I think you see there, the catch tank is outside, the fuel is there. It goes down to the bottom, and then it's there, and you can suck it with the fuel pump. Maybe it's from the geometry, it's a quite easy working thing. But your fuel tank has overall height from maybe for the package not the best. And then you see there, for example, with the new idea, just put a catch tank inside. But the fuel is not running to the catch tank because it's on the same level. But then you need some intelligent things, for example, some claps which the fuel goes inside and you can catch it, or you can use some foam or all such a stuff. But like it's described, I don't want to read all the words, but it's easier, and it's not so complex. You need not so much ideas, not so much testing. But with the inside one, you have a really big advantage in the height and lower COG. And a race car is quite tight, and therefore, for example, now you can use there for battery, for ECU, or for other low voltage stuff. And do this. And maybe if your fuel tank is about, I don't know, 5, 6, 7 liters, it's also weight, and you need some stiff holders there. And this is quite easier to put in a monocoque or a steel frame. Now go on to dynameters. At the beginning I want to talk a little bit different types of dynos. There is a drag dyno, where you can drag the engine. Then a roller chassis dyno, engine test bench. And then there are different component test benches, and for example swivel test bench. But I want to talk about maybe the common three ones. You see there some first impressions. You see there an old motorcycle. It's the race engine is inside it. It's a stock motorcycle, and with this you can analyze the mapping, the ignition, all the ideas from the OEMs, and then you can optimize it on your way. This is a picture from a test bench. Okay, a track dyno, like the name says, you can track the engine. You can track the engine with a eddy current brake and a small e-machine, because you see there is the eddy current brake, and the eddy current brake just can brake the engine and not track it. But yeah, if you have such an old dynometer, it's no problem. You just can adapt there with a small clutch, a small electric engine with a belt, and yeah, you're possible to track the engine. For example, for in-run it's also important that you see the oil pressure is there, and if you see the oil pressure is there, then you can go on with the first fire and put in the fuel. Then there may be a more luxury version is you have no end current brake, you have a track dyno with an asynchronous machine. Then you need no adaptation, because with the asynchronous machine you can track and brake your engine plug and play. And something special, I don't want to talk too much because it's quite tricky, but just for our outlook, you can also use a track dyno with nitrogen charging. I have there a picture, which means it's quite special. You have there, it's an intake system out of steel, and you put in there nitrogen, and you get it out of the exhaust. And the special thing is, for example, it is built out of steel because you have 1, 2, 3, 4 bars nitrogen inside, and 4 bars is not so nice for the very prototype one. And the benefit of this one is that you have there, if you track the engine, maybe you have only 10 or 20 bars compression camber because you have no combustion. But if you use the nitrogen charging, then you have 100 bars, for example, in the combustion camber, and you can test your conrod, your bearings, and all this stuff with a track dyno without combustion. There are some words too. With a track dyno you can make a mechanical in-run, you can test different components, and yeah, with a nitrogen charging you can operate under load. This is the special thing. The big pros from a track dyno is that you can test early in the season, early in the winter, because you need no injection, ignition, no ECU, and therefore it's quite easy to build up because it's not so complex, and you save a lot of money, for example, because you need no fuel and you need not so much sensors for analyze. Yeah, maybe the cons, it's not completely realistic from the temperatures, and it's not so much emotions, because there is no red exhaust manifold, there is no noise, but it's a quite important tool for early testing. There is an impression we can see that it's a in-run on a track dyno, and you see the different colors, and each color is 10 hours more running in the engine, and therefore you see the blue one is the complete new one, and maybe if you go on an event, maybe you are on a yellow one. But if you have a in-run on a dyno, you can go on a red one, and you save there, for example, 1 Newton meter. This Newton meter you just get for free. It's just the in-run, but you have not the time in the car because you have not the kilometers and so on. Then from the track dyno you go to the engine test bench. Yeah, you have combustion, you have more complexity, you have more opportunities. Maybe you need all the sensors, all the wiring, and you can do there your base calibration. A big pro is that you have all the realistic temperatures, all the realistic gas exchange. You can do what you want. It's like the engine in a car, but you have more freedom, you have more place, and you have more equipment. Yeah, maybe the disadvantages, it's quite expensive because maybe you burn sometimes some sensors, you need a lot of fuel, and it's quite complex, and it's a lot of time to build up. Sorry. Yeah, and you need a lot of time to build up your engine on a dyno. There are some impressions. You see there, for example, the intake system. It was disassembled because some optimization. You see there different softwares. Okay, if you now go from the the engine test bands to the roller chassis dyno, because you see there are some pictures. You have the opportunity to go with maybe the car on the roller chassis dyno or with the motorcycle. This was with the Formula Student race car for calibration, and this was with the OEM car, motorcycle, just for understanding and to get the first. Yeah, you see there a fan to cool it down because of the high temperatures, and you see there it's a plug and play adapted fuel tank, because we have to remove it from the motorcycle because of some measurement techniques, and the engine is under the tank. Okay, roller chassis dyno. The big advantage is you have the vehicle influence, which means you have your voltage, you have your sensors, you have all the stuff from your car, and it's not so steady state like in the dyno. In the dyno you have the ECU and all the stuff with 12 voltage, you have 12 voltage or 13. If you go in a car and you have some problems and you go drops to 10 or what else, then it's more realistic with the car. The process, you have your overall system, and you can test also everything. For example, you can also test your real drivetrain, you can test your exhaust system and so on. Maybe the cons that you have, pay attention a little bit. For example, if you go on a roller chassis dyno, I changed often the aluminum lightweight drivetrain and final ratio to a steel one. Because if you're one day on a roller chassis dyno, maybe you kill your complete drivetrain if it's lightweight out of aluminum. Therefore, put in a steel one. And if then you go to testing, put in your aluminum one. Okay, some words to measurement technology. Like at the beginning, I tell you, I call it slow and fast. This is just a nomenclature from my way, but what I mean is you have the slow measurement technologies. You measure some temperatures, pressures, lambdas, and all this stuff. You see there's some examples, because you want to understand or you want to compensate the pressures and the temperatures. And then I call the fast one. Fast one is especially the indication. Indication, you measure the intake exhaust and the combustion chamber pressure, and you measure it, for example, every 0.5 degree of crank angle. Therefore, this is the fast one. At the following, there are coming more and more pictures to understand the indication a little bit. At first, I call it must-have. You need, for example, for the synchronization, that your engine is running, you need cam position, crank position, that you know where is your camshaft, where is your crankshaft, where is your top descender, and so on. And for monitoring, for your ECU, for your compensation, you need, for example, some water and some water temperature, maybe oil pressure, also to control your engine, that everything is safe, that you're not blind. And for mapping, for example, natural aspirated engine, we talk about alpha N. Therefore, you need your rev and your position of your throttle. Then on top, nice to have is, for example, indication. We talk later. You can measure different pressures. Maybe not in a car, because it's quite tricky with the package and with the place. And yeah, you can measure every temperature you can imagine. For example, the airbox, fuel, in front of the radiator, after the radiator. You can measure your clutch temperature. Yeah, I think if you have a problem or you want to analyze something, you can measure it, but you don't need it. Then it's also like the pressures or what else. You can measure all pressure, or you can also measure this pressure which you're interested. And yeah, cylinder selective lambdas, oil flow. I think it's up to the calibration, up to the dyno, which is necessary, or which measurement technique you have and you use in the right way. Yeah, this is an example for the synchronization. You see there, this is the trigger wheel from the crankshaft. It says 60-2. From the camshaft it has only 1. And then it's synchronized. Then you see, okay, there is the one gap, there the other gap. The engine is possible to run. Okay, a little bit about indication. I think it's important for your calibration that you know where is your top descender. It's not so easy, because you can put in some screwdriver and see, okay, there is now our top descender. But for example, if you made a mistake out of 4 degrees with your screwdriver and with just for a manual test, then this 4 degrees is a mistake for the ignition, for the injection, and for everything. 4 degrees is maybe a quite big gap at the top descender, because yeah, if you know, for example, the 50% burn duration, it's up to you from the books. It's 8 degrees or 9, and there you have a mistake out of 4. It's quite big. Therefore, you can determine your top descender with a capacitive determination. It's quite a cure, but it's more elaborate. Or you can just make it a drag curve. With a drag curve, maybe it's a problem that the green one, you drag your engine with a sensor inside, and then the maximum, because of wall losses and heat losses, is in front of the real top descender, the mechanical one. And then you need to know the thermodynamic loss angle. If you know this, you can do it in this way. Otherwise, maybe at the first time you have to do it with this capacitive top descent determination. You put it in, and then at the end of the day, if the gap between your measurement tool and the piston is the smallest one, you have the highest voltage, and therefore you can analyze or you can measure where it is, and then you see there it's a cure up to 0.01. This is also, I think, quite tricky, but just for understanding that there is a possibility to do this in this way. Okay. Then a little bit motivation. What is engine indication, and why maybe you can have a big advantage. You see there, this is the stock spark plug. You see there you put in a measurement spark plug. You also have the spark function, and you have inside a pressure sensor where you can measure the pressure of the cylinder of the combustion chamber. And you need to determine the crank angle, because you want to know which pressure is at which degree crank angle. This is indication. Yeah, like it's written there. Then you know, for example, the piston is a top descender, or it's the valves are open, and then you can measure, for example, a PV diagram, and you know exactly at which degree crank angle, which pressure is in the combustion chamber. Then the benefit, because it's quite expensive and you need a lot of knowledge to implement it, but there's maybe an advantage that you efficiency, you go to H50, 50% of combustion is of mix air fuel mixture is burned down, and you want to control knocking. But at the end of the day, there are some numbers. For example, you want to finish, because to finish first you have to finish. Therefore, I made some analysis that you have peak torque and peak pressure. And you see there, for example, you have 100% torque, 100% peak pressure. Maybe the 100 bars are not so nice for your main bearings, for your conrod bearings. Now we go there, we have 75% performance. Therefore, we lose 2.5% performance. But we have reliability, if you can call it reliability, of 15% gain or win. And this then is, for example, also quite important for the understanding to save your engine, to save your resources. Here is a possibility. If you have no measurement spark plug, then it's some experience from older years of my 4-cylinder engine. You can put there in holes, then weld in some adaptions, spacers, and put in there some sensors, and then you can measure it with a universal sensor. This is a picture for the CAD analyze. Just cut your cylinder head. Maybe you have a broken, you have an old cylinder head. Just put it in some parts. And here is why the big effort, because you have to check it if everything is proof. You have to machine it after this. But you want to have a cylinder selective pressure signal. Therefore, on each cylinder, you have the possibility to measure and to understand your combustion chamber. And you see there, this is knocking, because at the first day, I just have a sensor on the first cylinder, but the force was knocking, but I don't see it. There was no chance, and the engine broke. Okay, we have to go on because of the time, I see. Some words to simulation and validation. This is maybe the line of action. You have some measurement on the dyno, you put in the values in simulation, then with the simulation, you can go to validation, and after this, maybe circle or half circle, you can get new components, put on the engine or dyno, and then yeah, you can make the evaluation and your check of the, because a simulation is quite important, but if you don't validate it, you're not sure if your simulation, your factors are quite good. This is just a picture of a 2-cylinder or a 4-cylinder simulation. This was with Ricardo Wave, this was with GT Power. Yeah, just build up your simulation model, put in your torque, put in your alpha K coefficients, your geometries like your runner, your cylinder head is, put in all this stuff, and then you can get out the output, how your torque is changed, for example, if you change your airbox. This is what I mentioned, the red ones, for example, is the torque, and yeah, the small stripes is the simulation, and the one line is the dyno measurement, and you see there are some differences, but this is because of transient, this is because of temperatures coefficients on the dyno, but at the end it's a quite good tendency, because sometimes you can have a simulation like it's this way and your reality is there, and then you need some more and more optimization of your simulation. Then here is a small example of validation. You have there with a software tool, it's Lotus Concept Valve Train. It's just one tool. You get out a minimum clearance of your valve up to piston. Yeah, and but I don't believe the simulation. I always want to check it. Therefore, I build up the engine with this simulated components, then put in some plastilene, and then track it with a wrench from hand, and then you can see, okay, the clearance is 0.9, simulation is 0.75, it's on the right side, everything is safe, and it controls the simulation. It's quite simple, but it's quite important. And then you see there it's static, because it was just with a wrench, it's maybe 1 turn per minute, and then you want to have the dynamic clearance. Yeah, you simulate with all your forces. You need your maximum ref, you need your mass and your gas forces, and then you can simulate this. And then you have a deflection of your conrod, for example. It lengthens at a high ref, and then you see there static clearance, then the lengthens, and then you have a dynamic clearance. Yeah, and then you can say this clearance is too big, is too small, and then you can change your hardware components, and you have a control. Okay, then I think the last big chapter is the calibration. It's quite important. You made your base calibration on your dyno for example, Formula Student, for different disciplines: axle, skid bed, autocross, endurance. And the endurance, you can go rich or lean, it's up to you. You want to go faster, then you can go, for example, up to 0.9, 0.85. Or you want to go lean, you want to go to efficiency, you want to win efficiency, then maybe you have to go to a leaner mapping. Okay, we talked about the dyno types. This is just an overview. I call it a 3-step calibration, because I start at a track dyno. I have a first in run, I can check the components, I can check the oil pressure. Then we go on an engine test bench. This is this picture. This is from the current Esslingen engine. There is some special measurement technique. There is the engine on site with some different changes. And yeah, you can make your base calibration, you can make all your compensations and all this stuff, your validation. And at the end of the day, like mentioned before, then you go on the roller chassis dyno, where you can go with the car, and then have the overall systems with the realistic, all the sub stuff. Okay, there is also picture. We have this from the test bench. It's the other test bench. It was the old one with all the stuff. You see there, which is quite important. You have a dyno control. Dyno control, which means you can track, you can brake the engine, just for control for the engine, for the dyno. Then you have there the next laptop for the indication system, for the pressure technology. And here you have, for example, in-car, the ETAS tool. It's one possibility for calibration of the engine of the ECU. Okay, just some basic rules, or maybe some hints. If you want to calibrate or to analyze your engine, quite important is only one parameter change at the same time, because if you change two, for example, and one is good and one is bad, at the end of the day you have maybe no benefit or no disadvantage, you are at zero, but yeah, you have two changes, therefore only one change. Then the compensation integration is quite important. Do this step by step. Compensation means, for example, your voltage drops. You can simulate it, or you can do it on a dyno. It drops from 13 voltage to 12 to 11 to 10 to 9, and then yeah, your fuel pump, for example, gets not enough fuel inside. Therefore, you have compensate your voltage. You have compensate your air temperature, because if the air is getting warmer and warmer. For example, you have an event in Russia and you have an event in Spain, then you need a compensation of the air temperature. Yeah. And at the end of the day, I say one series of maps is no series, because maybe you have some something which is not clear, or you have some average which is not on the best way. Therefore, always make two measurements. Then you can control it. If the gap from the two is too big, then make the third one. Okay, here is some at the end some overview, or we can see some measurements from the dyno. You see there, yeah, a lot of numbers. But at the end, what I want to say with this diagram is you have a relative torque. This is the red one. You have a brake mean effective pressure. You have a BE, which is up to you with your fuel consumption. And this is the combustion duration, how fast the combustion is. And you see then there the two lines, and you can then imagine, for example, like it's written down there, that for autocross, for example, you go to a lambda 83. It's just some modification of one engine. At the other engine, or maybe at the other intake system, it also can lambda 0.84, but maybe it's in this range. Yeah, you have your maximum torque. And maybe fuel consumption is not important for qualifying for autocross. And your combustion duration is quite fast. Then you go, just for example, to endurance. You want to save fuel. And you see there, you have maybe up to 10% less performance at lambda 0.95. But you see there, the advantage in your fuel is quite high. Therefore, yeah, you always have to look, what do you want to do? Do you want to have a high performance in the qualifying or in the axle, or do you want to save fuel and put the engine in the right way? Then an example for a start calibration. A start or restart is quite important, because if your car is not starting, you cannot test, you cannot get some measurement data. And you see there, this is the ref. You see like a traffic light. The green one revs up very fast, then the orange one, and the red one is the slowest. But it's hard to say, because if you have this revving up, you have calibrate your start. But for doing it, I use there, for example, the indicated mean effective pressure. It's some value from the indication. And then you see there, okay, for example, the orange one and the red one, it drops, which means combustion, it sucks a little bit and it's not working on the right way. And the green one is ramping up maybe in the best way. This is just an understanding or some control of your start optimization. And then some transient calibration. Because on a dyno, we talked about the steady calibration. We go to 5000 RPM, throttle position 50, 40, 70%, do the base map. And now we talk about transient calibration. You see there, it's shifting. It's 150 milliseconds when the torque drops and the torque is back on the same level. It's this way. It's the same picture, just with the optimization shifting. And you see there about 75% advantage, because if you go there, for example, you have ignition and injection. You put the ignition is quite fast. You put them back to -20, and there, for example, you put it only back to 0. It's enough that the torque is out of the gearbox, and you can shift in a sure way. And yeah, this is optimization. And the injection is quite slower than the ignition. But you just cut it also because otherwise all the fuel goes to the oil, and you save also fuel during shifting. Okay, this was all the papers. I think yeah. Thanks for your attention, and I hope you get an overview over your possibilities of dyno and engines. And feel free to ask now all your questions.
There's a question from my side.
Yeah.
How many hours your team spent on dyno?
Yeah, it depends a little bit up to the year and so on. Yeah, I would say maybe I was the engine team leader for 10 years in Esslingen, and there were some years we have no dyno, we have no engine test bench. Maybe we have maybe 2 or 3 days on a roller chassis dyno. Maybe it's not so much time, but it's not the first year of the engine because it's not possible to do all the calibration in 3 days on a roller chassis dyno. It's maybe only optimization. We changed in 17, 18, and 19. We used in 3 years 3 different engines with a supercharger, with 2 cylinder, with 4 cylinder. And there you need, I would say a lot of time, and maybe I would say up to 4 weeks. But for 4 weeks that the engine is running, that everything is compensated and maybe smooth in autocross and endurance. And then the next year, or maybe in the winter, or maybe sharp before the events, then you have sometimes maybe the problem is not the time which you're running the engine on a dyno. The problem is always the work before, all the adaptations, all the sensors. I think if everything is working, then you can do a lot of things in 2 days. But if everything is working, maybe you need 2 weeks. Yeah.
Yeah. Okay. And you talk about many topics here, many moments. But if, for example, we will talk about small teams with very limited resources, and I mean with a small amount of students, which moments are more important, and how you in which proportion you split your time
Yeah.
depending for different systems.
Maybe like I mentioned a little bit, there is measurement technique and there is indication, all this stuff, or own crankshaft. This is maybe nice to have. Yeah. In my opinion, I hope that this is your question. In my opinion, you, for example, choose a good engine, a good base engine, because it's from the package and it's lightweight and maybe it's available and not so cheap. Yeah. And you have this base engine. Then you made your base calibration. Don't know, the ECU doesn't matter. And maybe the most important things, in my opinion, is that you have a sure oil pressure. Because you have good oil pressure, you don't burn down your engines. And the most important thing for performance and efficiency and for maybe the overall adaptation is the intake system, because of the restrictor. Therefore, if you have not so much, call it resources, I will say use maybe the best engine you can get, and then put in a good intake system, and be sure that your oil pressure is fine, and then made your calibration. It was like the way you want to know it, or?
Okay, Markus, sorry, can you repeat the last few sentences because of the connection problems?
Was this the question which you want to know in this way? That you maybe put some effort in the intake system because it's good for the overall performance and to the adaptation because of the restriction. Be sure that your oil pressure is fine, then you don't burn down your engines. And maybe use the best engine. Just for example, we need new pistons and new crankshaft and all this stuff because the engine has the wrong displacement. But we want this engine because we say, okay, it's lightweight, it's the best engine which is available, but it's a lot of effort and a lot of resources.
Mm-hmm. Okay, thank you.
If we would like to start building dynamic stand, what we should start from?
Sorry, I don't understand it really.
If we would like to build a dynamic stand, what we should to start from?
Yeah, maybe it's not so easy here, but I would say if you go maybe to dynamic things with maybe a calibration or to the maybe to the all dynamic things, you start with maybe a good static one, because if you have a good static base, you know all your values and all your components, and then with the dynamic one, I would say start with small changes, and then you see where is your benefit, or you're in the right way, or in which direction was your main question.
Ты про стенд спрашиваешь?
Ну, да, просто.
Ну, стенд — это тест-бенч.
Test bench.
Да. Ну, перезадай еще раз. Просто.
Yes, test bench, if we want to build it.
Yeah. If you want to build up maybe the test bench new, yeah. Okay, maybe
Yeah.
I would say you need a brake, like I mentioned a little bit. You can use a adding current brake. Then you cannot track, but don't need. It's enough if you can brake. You need a brake. With this brake, you can brake your engine to the RPM which you want. Then you have the RPM and the load. And then maybe you need, like I mentioned, the necessary things, like you need the ref, the throttle position, and maybe temperature and pressure of oil and water. That you can control that everything is in the right temperature, pressure. Then you need from the brake, you need a shaft. This shaft goes to your gearbox of your engine. Then maybe it's important, because a normal brake or asynchronous machine or what else cannot rev up to 10,000 RPM like a Formula Student engine. But if you have the brake, then you have the shaft, and you go to your gearbox, then you can use, for example, the force gear, and then you can handle all the RPMs. Yeah, and you need maybe some adaptation that you can put on your engine on a dyno. It means there's the brake, then there's the shaft, and then you need some frame or what else where you put in your engine. Then it's fixed. And then you can fire.
Yes, thank you. Hello, Markus.
Hello.
My name is Vladimir. I'm from Toleti, from Toleti racing team. And my question is, what is a better way to provide traction control performance, by using a mechanical throttle or an electrical one?
Yeah, it's quite interesting. Maybe I would say if you have an ETC, then you have more possibilities and more freedom to handle it, to adapt it, or what you want. In my opinion, it also works with a cable adjusted throttle. Maybe the hardest thing is that you have if you want to do a traction control, for example, you have all these. Yeah, you have the two which are not driven in the front, for example. You can average, then the rear average. Then you have this slip of the which you want to kill with your ignition, for example. Maybe more tricky is that you have you need informations about your tire temperature, about of your mu of the test track. Maybe back to your question, with the cable adjusted, you can realize it. You can do it because you don't need ETC, but you have more possibilities and more degrees of freedom with the ETC. My old team, we do it with a cable adjusted. The Esslingen, for example, has no ETC up to now. You can do it with cable adjusted, but with ETC you have a lot of more possibilities, but you also need a lot of more maybe effort or some more parts.
Okay, thank you.
Good afternoon. How much does the architecture of the system after the dynamics of the car? I mean, stay of the stock is the system or make custom?
Okay. You want to know the exhaust system? Is maybe how big is the influence or how big is the advantage if you make it completely customized, or?
Yes.
Okay. Yeah, maybe for short practical answer, I would say the exhaust manifold, the primary, which means that the directly pipes from the cylinder head, they are quite important for the gas exchange, the diameter and the length and so on. Your muffler, maybe you can buy one. Because for your gas exchange, for your all your simulation stuff or for your waves, is the pipes, the exhaust manifold is quite important, and then the muffler, if you have a 4-cylinder engine, for example, then the secondary and the tertiary pipes, the influence is not so big, and you can buy, for example, a muffler because it works, it's lightweight, and you have a good back pressure. Make your own because you're happy or
Sorry, Markus, can you repeat one more time because we lost your last sentences about the muffler?
okay, yeah, okay. I would say you can you have to build your manifold customized, because then you can use the optimum package for your race car, and you have the optimum lengths and diameters for your gas exchange. And for example, you have a 4-cylinder car, the primary pipes are quite important, the secondary and tertiary are not so important, and your muffler you can buy because then it's reliable, light, and the back pressure is normally also good. Yeah, therefore primary pipes, exhaust manifold, important to make at your own, and the muffler you can buy or you can use an old one.
Можете перевести, я просто не успею за ним.
Короче, выпускной патрубок надо производить самостоятельно, поскольку его диаметр и объем крайне важен для правильного газообмена. А уже дальше глушитель не важен, и, в общем-то, можно купить какой-нибудь подходящий, либо использовать стандартный.
Thanks.
Okay, yeah.
Hello, Markus.
Hi.
My name is.
Hi.
Can you hear me? I'm from Yekaterinburg. It is on the border between Europe and Asia. So my question is, what is your opinion? Which parameters driver should check during the endurance, and which parameters he should calibrate during the driving? I mean parameter of engine.
Yeah. Yeah, maybe it's not so easy because as he can have a look and can control different parameters, but it's not so easy to change parameters during the race. Yeah. In my opinion, where the driver has to have a look on oil pressure, water temperature, lambda. Maybe this I call it control stuff, because then he know, okay, the temperature, the pressure, the lambda, everything is in this gap which I want to use the car, and it's on a safe way. Yeah, maybe, but on the other side, he cannot change it really, because if there is some issue with fuel pump, with lambda, with the oil pressure, with the suction pump, he cannot change it really. Yeah, and maybe in my opinion, it's also hard for a Formula student driver.
Bluetooth connected.
Sorry, could you repeat the last sentence as well?
Yeah. And in my opinion, it's quite hard for a Formula student driver to drive and to have a look on all these values, because his drive cannot handle all the parameters. what in my opinion is a quite good solution. I think a lot of teams use this. That you have a telemetry, and then one guy is standing there, I don't know, at the grandstand with the telemetry and sees everything, and then just have a CB to the driver, and then, for example, I can say the Esslingen car, oh, I see, we have a problem with the temperature, I don't know why. Maybe the last 3 laps we go only with 30% throttle because we want to finish with a good temperature. Therefore, in my opinion, is control all the values, but do it with the telemetry. Then the driver can drive as fast as possible. You say that the driver some accident or some happened with the values. What you have to do?
So I hope I understand you correctly. Thanks. So, and one more question. What engine did you show us?
Okay, the 4-cylinder engine was a CBR 600RR. I used this from 2010 up to 17. And the 2-cylinder engines, the motorcycles were Yamaha MT-07.
I asked you about four-cylinder engine because we have the same. Thanks a lot. Ну что, все? Просто нет больше. Okay, Markus, it seems like no more questions so far.
Okay.
And so we also run out of the time. So
Yeah.
Very big thank you to you. It was really interesting, especially for me because I'm not an engine guy. So thank you.
Okay, yeah. Thanks also from my side. I think I would give you a short overview over the different topics, and yeah, if there are some more questions, maybe you can contact me, and then we can handle this.
Yeah, I will. If there will be a question, I give you a contact.
Then you can write me, and I answer this. Okay,
perfect.
then have a nice day.
Thank you very much.
Bye.